Trusted memory, or software-based off-chip memory protection for RISC-V trusted execution environments. A paper authored by myself, Dayal Lee, David Kolbrenner, Kirsta Izanovich, and Don Song. So, what is trusted memory? What am I talking about? Well, this paper is going to discuss securing data or code against any sort of snooping or reverse engineering by an outside party, including physical attackers. So that includes securing data against the user of the actual hardware that they're in possession of. So why would you want to do this? You might want to store cryptographic keys. You might want to store personally identifiable information, proprietary information, or you might just want to obscure your code as a form of defense in-depth mechanism so that reverse engineers can't get access to it. And so today I'm going to discuss two different security domains in the form of on-chip and off-chip system memory. So on-chip is literally the memory of the system on-chip that's integrated into whatever board you're using, in this case, Hi5 Unleashed. It's literally the L2 cache configured as RAM. And so this one we presume as secure because, well, in order to crack that memory, you would have to decap the chip, which is difficult, expensive, and it's often destructive. Whereas on-chip memory could be tapped by a determined hobbyist with the right tools and expertise. Now, on the flip side, on-chip memory, although it is much more secure, it's much more limited in that it has only on the order of megabytes of storage, whereas on-chip memory or off-chip memory has thousands of times that storage. And this is just a 2-scale visualization. You can see for yourself, on-chip is much, much smaller. And also, what kind of determined hobbyist can tap into the off-chip memory? Well, in this case, it was Neymod, who was an old-school Nintendo 3DS hacker. He was trying and eventually succeeded in dumping the Nintendo 3DS memory by tapping into the actual memory bus like this. So it's definitely possible by a determined enough hobbyist. And so the problems we face when it comes to memory leaving the on-chip region is confidentiality and integrity against a physical attacker. Confidentiality is pretty simple. It's can the attacker read your data? And integrity is whether the attacker can actually modify your data without you being able to see that they modified it. And so today I'm going to discuss Keystone framework, which is a trusted execution environment. And that's the system under which this whole scheme is going to be operating. I'm going to discuss the prior art in Intel SGX. That's an existing memory encryption and integrity protection scheme that exists in hardware. I'm going to discuss protected paging, which is the actual system by which we implement our software routine. And then I'm going to discuss evaluations and a conclusion of our system. So we're operating under Keystone, which is a framework for trusted execution environments, as I mentioned. And so basically, Keystone provides secure enclaves in an extensible and customizable, as well as open source software-based approach. And that open source software-based approach is especially important for actually providing these two values right here, because the fact that anyone can change the parameters of Keystone at any given time are exactly what make it so flexible, and that's why we chose it for implementing this sort of memory protection scheme. Core to Keystone's guarantees is that it manages to divide the system into two worlds, the trusted and the untrusted worlds. And so trusted is where enclave memory resides, and that in turn is where the sensitive app enclave, code, and data reside. The untrusted world is where everything else lives. The operating system, any other apps that are running on the system, those are untrusted. And so this division that we accomplish with physical memory protection, which is a RISC-V feature, gives us integrity, confidentiality, and it also gives us remote attestation, which is a concept that basically means an outside observer can verify the system is running correctly. And so why might one want to use a system like this? Well, consider running this program a machine learning training or inference model. and you want to protect it from any sort of competitor or even the cloud provider that you're running on from being able to see your training data or any sort of other secrets that might lie in your algorithm. Now, it's worth noting that this sort of division between trusted and untrusted worlds, by default, still doesn't allow Keystone to protect against a physical attacker. And that's because physical memory protection doesn't protect against physical attackers. It protects against software attackers. And Keystone works perfectly well for its use case, which is preventing software-based attacks. But as I previously mentioned, hardware-based attacks are more complicated. Keystone can enable the use of on-chip memory for the enclave memory, and that protects against hardware-based attacks. But by doing so, you limit yourself to a very small amount of on-chip memory. And so what we'd like to do is prevent on-chip memory from being exhausted as quickly as it is. And the way that Keystone currently does this is with demand paging. But this breaks down the security barrier for hardware-based attacks, because now we're storing secure enclave memory that's on-chip in off-chip memory. And off-chip memory, we've already seen, is vulnerable to attack. And so now the problem becomes confidentiality of pages, because we're demand paging our on-chip memory, and the integrity of the pages. And so we'd like to see whether an attacker can read or change the pages after they move off-chip. The solutions to that are pretty simple: encryption and hashing. So we just like to encrypt any outbound pages and hash any incoming pages and check their hashes against a previously stored value. And there's some precedent for this approach. Intel's Secure Guard extensions, which is available in commodity hardware today, provides a solution to these two problems. Intel operates on a 512-byte block granularity, but it provides AES and counter mode in 128-bit keys, version counters for replay protection so that no page can be replayed into the location it previously operated in. It provides Carter-Wegman message authentication codes for protecting the integrity of off-chip pages, and it stores those codes in a Merkle tree, and we'll get to what exactly Merkle trees are in a bit. So this paper provides a software approach that we can use on any sort of commodity RISC-V hardware that has physical memory protection and is able to run Keystone. And so this provides confidentiality through 256-bit AES, 256-bit SHA, and it operates on a page size granularity that's a fair amount larger than Intel's scheme. But that's a constraint that we can't easily remove. As for the other two constraints, we're using SHA-256 and AES-256. That is easily configurable if we decide, for example, that the security guarantees of 128-bit aren't enough, or if we decide that 256-bit is too much, we can always change any aspect of this because it's implemented in software. And so this is the scheme itself. It operates around this very simple page swap mechanism that you can see encoded in this loop. And the very first thing we do is we take the page, the source page, that's being paged out or evicted, and we run it through SHA-256, and then we encrypt it. And then we store those two values for later. Then we take the page that's being paged in, we run it through an AES decryption function, and then run the hash of the decrypted output. Now, the order of the hashing before or after encryption doesn't really matter because we're salting these hashes with two different values. We're salting it with the actual address that we're paging, and we're salting it with the page counter to prevent replay attacks. So there's no sense of being able to infer data from these hashes. And then we're going to actually insert the outgoing hash into our hash store, which is represented with this tree. And we're going to query our incoming hash from the hash store. And this query is going to make sure that nothing has been modified in the incoming page that we haven't been able to track. Now, the fact that we're using a tree here is very important, and it has to do with the fact that Intel and we use Merkle trees for storing our hashes. And the reason that we don't just use an array of page hashes in on-chip memory is that it would be wasteful. We don't have very much on-chip memory to work with. So we actually move the bulk of it off-chip. Now that begs the question, if it's off-chip, does that mean we can't trust it against a hardware-based attack? Well, it turns out that what you can do is provide confidentiality and integrity with this hash store, despite storing the majority of it off-chip. As for confidentiality, it doesn't really matter if people can see the data that's stored in this hash store, because cryptographic hashes in this case don't carry any information. They're salted, and so you can't infer anything about them. Now, as for the integrity protection, we solve that with another layer of hashing. Instead of just hashing the page that we're trying to bring in, we hash the entire page store as well. And so we can keep that root hash in on-chip memory, and we keep the rest of it off-chip. And so this is our original scheme where we had the hash store in the trusted on-chip memory. And what we want to do is we want to move it off-chip, because on-chip memory is too valuable to be using for that purpose. And so what we do is we take the hash of the entire hash store, as I mentioned, and store that in the root. And the root is stored in on-chip memory. But then we run into the problem that hashing the entire store is a pretty big waste of CPU cycles, because we're doing that on every page fault. And so what we can do is we can split the hash store in half, and then we can hash half of it when we go into a region of the hash store that contains the data that we're interested in. And we can hash the other half otherwise. And then we can propagate those hashes back up to the root and have the root hash be itself a hash over both these different regions. And so that cuts our overhead in half, but what we'd really like to do is do this recursively up until the point where we can't split any longer. And the tree that you create by doing this is called the Merkle tree, and that's exactly what we were referring to in Intel's SGX and in this scheme. Now, if you take this to an extreme, you get a binary search tree, and that's exactly what we use in the software-based approach. But of course, you can configure the depth of your Merkle tree by configuring the size of these blocks. And there are some trade-offs here. What's constant is that you only need a specific amount for your root hash. And that's going to be the size of your hash in bytes, in this case 32. But as you increase in depth, you start needing more and more hash passes, which is important if your hash has startup latency. And it needs more and more insecure memory. As you can see, we start creating all these intermediate nodes. But we want to actually extend this hash tree because with every intermediate layer that we add, we have to decrease the amount of bytes that we hash on any given page fault. And that's just because we're only going up one of these branches at a time. And so by implementing this approach, we show that it's feasible to have a software-based memory protection algorithm, although it doesn't introduce a significant amount of overhead. Of course, there are optimizations that we can make, and there are parameters that we can tweak. Like, for example, we can decrease key sizes, or we can increase the block sizes. All these things represent security, speed, space trade-offs. And in general, we see that if we have some sort of efficient paging infrastructure, even our current unoptimized protection routines are fast enough to be usable for day-to-day purposes, depending on your application. And so this chart right here encodes the slowdown that we see over the baseline paging implementation in Keystone. And these benchmarks were computed over the RV8 benchmark suite, and we ran them with 1 megabyte of on-chip memory. So that's half of the entire available L2 cache on the High5 Unleashed platform. And we ran them with these different parameters of things that we enabled. So PI represents paging with integrity protection, PE represents paging with encryption, and PIE is both. And so we can see here that QSort and AES and even NORCs provide pretty reasonable slowdowns, but depending on your application, these can be acceptable. Unfortunately, in Keystone as it currently stands, paging represents a large amount of overhead that's added, especially as you increase the amount of memory that your application needs. And this makes sense. If you even use, for example, the Linux kernel, and you have to page out normal memory onto the disk often, you'll see a very big slowdown if you vastly exceed the amount of memory that's available. And that's what we see encoded here in especially these first few benchmarks. We see applications that use vastly more memory than is actually available to them, and so they see lots and lots of overhead from paging. And so we decided that protected paging is appropriate, but it's appropriate for security critical, speed flexible operations. And it's for ones that have memory pressure that's not easily reducible, but that still operates mostly around the limit of what's provided by the system. And implementing this whole memory protection system also lays the groundwork for other sorts of space optimizations that Keystone can pursue in the future. We can free up the L2 cache, and we can balance on-chip memory among several enclaves. Basically, the idea is if one of your enclaves is idle, you don't have to keep it resident inside of on-chip memory. You can push it off the chip and free up that space for other purposes. And in general, Keystone and this scheme provide a flexible approach for dealing with security, speed, and space trade-offs. They allow you, as the designer, to decide which IP blocks you need, and if you decide to omit them altogether, as in the case with currently available hardware, you can free up die area for other purposes. And you can use the current system on pieces of hardware that were never designed to be used with this. And then if you decide that you now have access to, for example, AES or SHA routines or any sort of hardware acceleration, you can drop them in instead of just using the software routines that are currently available. And so the idea is this one scheme is parametrizable over any sort of hardware configuration or software stack or speed, space, design trade-offs that you may want to make. And that's the real strength of having this implemented in software, is that you can decide to make these trade-offs without having to go through expensive chip validation, verification, retape outs, or having to buy a new set of commodity chips altogether. Thanks for watching, and please read the paper if you'd like to learn more.